Okay, here we go. We're going to do the crystal violet lab, right? So first of all, put your name and the date up here, and then in the procedure you put how much you weighed out, how much you diluted to, and how much further dilution you did. Crystal violet formula weight is 407.99, approximately here. Oops. The path length is 1 centimeter. The amount weighed, let's say it's 40.5, 0.0405 grams. If you want to know how many milligrams that is, you can say equals this times 1,000. That's 40.5 milligrams, right? Oops. The initial dissolution volume, let's say that was 50 milliliters or 0.050 liters. Pipette volume was maybe 0.001 liters, and final dilution is maybe 0.1 liters. Now, in order to get the spectrum in here, we're going to have to go to Canvas. We're going to have to go to Files, and then Lab, and then Crystal Violet Data. And for example, we can get the Thursday data here from Dan. This is just going to show us the file. What we actually want to do is come over here, say download, and it's going to put it in a CSV file format, and I'm going to specify the folder that I have for the Excel data files there, right? I'm going to save that. I'll put this up here. Now I'm going to go File, Open, and I'm going to go to Browse, and now I'm going to go to, from all Excel files, I'm going to say All Files, and then there's Dan, there's the dan.csv file there, and I'll open that, and here is the wavelength and absorptions for the 1 micromolar dye. So I'm going to highlight those, and I'm going to type Shift, Control, and down arrow. Then I'm going to Control C to copy that. I'm going to tab over here to the file that I'm putting it in. I'm going to click here and say Control V, and that will give me the spectrum, right? And if I click here, I'm going to move over the target here so I can see this, the absorbance spectrum. The maximum here is about 593, about 0.027. So -0.027 absorbance units, 593 nanometers. Now the moles of dye is going to equal the amount weighed divided by the formula weight. The initial concentration is going to be equal to the moles of dye divided by the volume of dye. The final concentration is going to be equal to the initial concentration times the pipette volume divided by the ball flask volume. And the extinction coefficient will equal the absorbance divided by the concentration. All right, so that's how we do that first page. Now that we know the extinction coefficient, and the concentration actually is what we need here. That's in cell E44 up here. What we're going to do is we're going to come over, and for epsilon we're going to say this is equal to the absorbance divided by $E $44. Right? And that $sign is going to make sure that as I propagate this down, the target will remain E44, even though the source is propagating down. So now I'm going to come back over here, and we will highlight this data set, drag it back over to the epsilon column, and there we have it. Now this epsilon is coming out way too small, but that's not important right now. What's important is because I just made these values up. I don't know what these students actually did, right? So what we can do here now is we can get along with the process of doing the uncertainty analysis on the data. So there's epsilon, right? So this guy is, I'm going to actually zoom out here a little bit, because this guy here will be equal to the extinction coefficient, right? That's just what that is, right? And then M is going to equal the amount weighed. Formula weight is going to equal that value there. V0 is going to equal that value there. V1 is going to equal that value there. V2 is going to equal that value there. Absorbance is going to equal that value there. Path length is going to equal that value there. Now, SM, that is going to be the uncertainty in the mass, and I'm going to estimate here that it's about 0.5 milligram. So that's 0.0005. Formula weight, I'm going to say 0.01, just a guess. And I'll make the volume uncertainties about 1%, right? So 0.0005 and 0.00001, 0.001. Absorbance is 0.0005, and B 0.001. Right? These are all guesses about the uncertainties. And we can do better, but for right now, let's just leave them as guesses. Now, dE by dm, according to the analysis we did in lecture today, this is simply equal to, oops, I have to take away one of those equal signs, equal to epsilon divided by m, right? dE by dFW is equal to epsilon divided by FW. dE by dV0 is equal to epsilon by V0. d dV1 is equal to epsilon by V1. dV2 is equal to epsilon by V2. dA is equal to epsilon by A. And dE by dB is equal to epsilon by B. And accordingly here now, S sub E is going to equal I'm going to type it up. Well, I'm wondering, I try typing it down here. Maybe that'll be a little easier to see. Hold on. This will equal the square root of the following terms one, two, three, four, 5, 6, 7. So 1, 2, 3, 4, 5, 6, 7 terms, right? And this first parenthesis will have in it SM times dE by dm. Second term will have SFW by dE by dFW. Third term will have SV0 by dE by dV0, etc. Okay, now I'm going to enter that, and I get about 38 per molar per centimeter. Formula text here is going to be equal to formula text, this guy, epsilon, that will equal this guy, and uncertainty will equal this guy. There's our final answer. Now, one thing we may want to do is we may want to name these cells so that Dr. Terrill doesn't lose his mind when he's trying to grade it. So what we can do is we can go to, on the Formulas tab, we can highlight the names and these guys, and we can say create from selection, okay, create from selection, okay, create from selection, okay, right? And now you can see here that that's SM, and that's dE by dm, right? That's much easier for your old teacher to recognize. Right? All right. So you see the symmetry, SM by D by DM, SFW, D by DFW, etc. all the way through. And this gives us a very reasonable answer of 38 per molar per centimeter out of 1,300, roughly 3% of the total. That is about what we're looking at here. And this is the report.